just in case. Okay, so welcome to week 12, question 1. A manufacturing company produces 2 models of a HD TV per week. X units of model A and Y units of model B at a cost in dollars of the following. So we've got this cost function based on 2 independent variables, X and Y. It is necessary because of shipping considerations that X plus Y is equal to 90. How many of each type of set should be manufactured per week to minimize costs? What is the minimum cost? Okay, so we have this cost function. We want to find the minimum of this cost function. So if I didn't really know about any constraints, I'll say, okay, let X equal 0, Y equal 0, boom, there's your minimum cost. Of course, there is some sort of constraint here. So whatever X and Y is, they must sum to equal 90. So a couple of things to take away from here. We've got a cost function, or a function in general, that has more than one unknown variable. In this case, we've got an X and a Y, and we've got some sort of constraint here. So given those two, we can actually try to solve this using the Lagrange method, right? So the Lagrange method, it does sound a little scary, but it can be broken up into a few key steps. So step 1, we're going to be formulating the problem, which basically means you're going to be stating to me what you want to achieve. So in this case, we want to minimize, right? We want to minimize some sort of function here. Our cost function has 2 independent variables, X and Y, which is equal to 6X squared plus 12Y squared. Okay. So we want to minimize this cost function subject to a certain constraint, subject to X plus Y is equal to 90. So subject to X plus Y is equal to 90. Okay. With our constraint, we're going to set our constraint equal to 0. So I'm going to bring 90 to the other side. So this becomes X minus, or X plus Y minus 90 is equal to 0. So there's our first step done. Our second step is we're going to be creating this Lagrange equation. So this Lagrange equation is going to be made up of 2 parts. Your independent variables, X and Y. So there's your first part. And this lambda per term. This is your second part. Okay. This lambda term actually has a special interpretation, but we're not going to really interpret it for this question. We'll save that for the next question. So this Lagrange equation is going to be equal to the function you want to minimize or maximize. In this case, it's this function. Plus lambda multiplied by your constraint set equal to 0. So we're going to move all this into the bracket. As so. Okay. So this is our Lagrange equation. We're going to expand it out. So this becomes 6x squared plus 12y squared plus every term here we're going to multiply by lambda. So x times lambda is x lambda plus y times lambda is y lambda minus 90 times lambda is minus 90 lambda. So this is our Lagrange equation. So let's maybe pause a little bit and just appreciate what this equation is all about. This equation considers our cost function as well as our constraint. So it's an equation that contains both our cost and our constraint. And with this overall equation, what do we want to do? We want to find where is a minimum. Okay, so how do we go about doing that? Well, let's maybe take a step back and talk about our previous few weeks in Module C. So our job was basically to find where is our function maximum or where is our function minimum. We know they probably occur where they have 0 slopes. In other words, where they have critical values, right? So how do we solve for these critical values? We found the derivative of those functions, we set it equal to 0, and we solve for x, right? So we solve for x here, or we solve for x here, for example. Okay. For this, it's actually a very similar story. We know this minimum point will probably occur where this function has a 0, or essentially a 0 slope, or critical value, let's say. So where this function has a critical value. Okay, so how do we find where this function has a critical value? Well, pretty similar. We want to find the derivative of this function, set it equal to 0, and solve. However, this function is a little bit more complicated. It has not only x as an unknown variable, but it has y and also has lambda. So how do you take a derivative of such a function? We're going to be utilizing what's known as partial derivatives. So we're first going to take the partial derivative in respect to x, and later on I'm going to do it for y and then for lambda. So let's take the partial derivative in respect to x. So how do we do this? Where there's an x, you're going to do it per normal, right? So there's an x here, you're going to do it per normal. Any other variable you're going to treat like a number. And what does that mean? We'll talk about it pretty soon. So here you do it per normal. 2 goes to the bottom, 2 times 6 is 12. X, the powerless 1, or implied 1. So this y squared, you're going to treat like a number. So like any other number, it will do something, right? So let's suppose y squared is a number, right? Let's say I'm going to make y squared the number 2. What's 12 times 2? 24, right? What's the derivative of 24? What's the derivative of just any number or any constant? It's always just 0, right? So y squared we treat like a number, and if it's just a number, derivative of just any number is just 0. Okay. As you can imagine, in order to even understand partial derivatives, you got to have a firm understanding on the partial rule. Oh, sorry, on the power rule is what I should say. Okay, let's keep on going. There's an x here. So the way I talk about this is kind of something like this. Derivative of x is 1, and like any other number, you treat lambda like a number. Like any other number, it comes along for the ride, right? And let's maybe explore this a little bit more. Let's suppose lambda is a number. Let's say it's number 3. So I'm going to put 3 here. So this will be 3x. What's the derivative of 3x? The derivative of 3x is just 3, because the derivative of x is just 1, and like any other number, 3 comes along for the ride. 3 is your lambda, right? So for example here, derivative of x is 1, and like any other number, lambda comes along for the ride. Okay, there's no x here, so all this is just a number, 0. There's no x here, so all this is a number, just 0. So we're done here. We're going to set this equal to 0, and in this case, you could solve for x or lambda. I will choose to solve x because it's usually the easier way to do things. But if you solve for lambda, you got to sort of adjust your root a little bit. And you'll see an example of that in the second question. In the meantime, I'm just going to move lambda to the other side. So this becomes 12x is equal to negative lambda. And we can solve for x by dividing both sides by 12. So x is equal to negative lambda divided by 12. Okay, there's our partial derivative in respect to x. Let's solve for the partial derivative in respect to y. So in respect to y. So our main variable of interest now is y. So there's no y here, or this is a number to us, 0. There's a y here. So we're going to do this as per normal. We're going to bring 2 to the bottom. 2 times 12 is 24, y, and the powerless 1. Right? The powerless 1 is just implied 1. There's no y here, this is just a number to us, 0. There's a y here. So derivative of y is 1, right? And like any other number, lambda comes along for the ride. There's no y here, so all this is just a 0 to us. Okay, we're going to set this equal to 0, and again, I'm going to solve for y here. So I'm going to move lambda to the other side. So generally, if you solve for x, you want to solve for y, right? They come as a combination. So I'm going to move lambda to the other side. So 24y is equal to negative lambda. Then I can solve for y by dividing both sides by 24. So y is negative lambda divided by 24. So we have an equation for x and y. We just need a lambda value to find those numbers for x and y. Okay, let's do our last partial derivative in respect to lambda. Okay, so our variable of interest now is lambda. So there's no lambda here, or this is just a number to us, 0. There's no lambda here, or this is a number to us, 0. There's a lambda here. So derivative of lambda is just 1, and like any other number, x comes along for the ride, right? Plus, derivative of lambda here is just 1, and like any other number, y comes along for the ride. Plus, derivative of lambda is just 1, and like any other number, negative 90 comes along for the ride. Okay, we're going to set this equal to 0. And here's a bit of a tip. This is just through practice. Every time you solve for the partial derivative of lambda, most likely you'll be subbing something into here. So I'm going to be subbing x into here, and I'm going to be subbing y into here. What's going to happen if I do that? Well, since x is expressed in lambda, and y is expressed in lambda, I'm going to have an equation all expressed in lambda, and hopefully by moving things around, I'll be able to solve for lambda. So let's do that. So x is now negative lambda divided by 12, plus y, which is negative lambda divided by 24, minus 90 is equal to 0. Okay, so how are we going to solve for lambda? I'm going to move this minus 90 to the other side, and I'll probably, since these are fractions, I want to get these bottoms to be the same. So you want to ask yourself, what's the common denominator between 12 and 24? Well, you can make 12 to look like 24, right? 24 is the common denominator here. So how do I get 12 to look like 24? I'm going to multiply it by 2. But here's the thing, I can't just multiply the bottom, I'll also multiply the top to keep things equivalent. So that's what we're going to do. Okay, so 2 times negative lambda is negative 2 lambda, divided by 2 times 12 is 24. And over here, I'm just going to get rid of these brackets. Minus lambda divided by 24 is equal to, and I'm going to bring this 90 to the other side, is equal to positive 90. Okay, now the bottom is the same, we can just add the top divided by the bottom. Negative 2 lambda minus lambda is negative 3 lambda, divided by 24 is equal to 90. I can get 24 upstairs by multiplying by 90. So negative 3 lambda is equal to 24 times 90. Okay, now I can get lambda by itself by dividing both sides by 3. So getting negative 3 to the other side, divided by negative 3 is equal to negative 720. Okay, so I have a lambda value. That was the actual value we needed, right? So now we can calculate x. x is simply negative lambda divided by 12, right? We know lambda now is negative 720. So we've got a double negative situation here. Negative 720 divided by 12. So double negatives, of course, just make a positive. This will give us a positive 60. What about our variable for y? Well, y is equal to negative lambda divided by 24, right? So now we've got, again, a negative situation. Negative 720 divided by 24. This will give us a positive 30. Okay. And we've got lambda already here, so we can actually now express this as a triple pair. So x goes first, being 60, followed by y, being 30, and then followed by lambda, negative 720. So this represents our solution, right? In other words, this represents our critical value, right? So notice here, we've only got one critical value. If we've only got one, we can actually assume that this represents the answer to the problem. So what was the requirements of the problem? We want to find what values of x and y should we put into here to minimize this cost function. These are our values for x and y that would do that job, right? So what is the value of this minimum cost? Into your cost function when x equals 60 and y equals 30, right? So your cost function looks like this: 6 times 60 square plus 12 times 30 square. That's going to give you a cost function that looks as, what does it look like? 32,400. There's your minimum cost. So here's the theory. Any other value for x and y, remember, they must sum up to 90. So x plus y equals 90. And you can see that's a good way to check. 60 plus 30 is indeed equal to 90. Any other combination of x and y, as long as they sum up to 90, will not get you a lower value than this value. This is your lowest or your minimum. Okay, that's part 1 done. Let's go over and, I should say question 1 done. Let's go over and do question 2, your second last question forever. Okay, here we go. A consulting firm for manufacturing company arrived at the following Cobb-Douglas function for its particular product. So we have this unit production function based on 2 independent variables, x and y. In this equation, x is the number of units of labor and y is the number of units of capital required to produce n units of this product. Each unit of labor costs $40 and each unit of capital costs $80. Okay? If $400,000 is budgeted for the production of the product, determine how that amount should be allocated to maximize production and find the maximum production. Okay, so what do we have here? We have a function we want to maximize. We can't just say x is a billion and y is a billion. There's your maximum. We have some sort of budget. Okay, so to tackle this question, we're going to follow those key steps. Okay, so step 1. We're going to formulate our problem. In this case, we want to maximize, right? We want to maximize this Cobb-Douglas function, which is equal to 50x 0.8 y 0.2. Okay, so we want to maximize this Cobb-Douglas function. Subject to what constraint? Well, subject to, we have some sort of budget of 400,000. How do we put that into an equation? Well, to hire one person or one unit of labor will cost $40. 40 times x will give you the total cost related to labor. Plus, to hire one unit of capital will cost $80. 80 times y will give you the total cost related to capital. Whatever x and y is must sum up to, in this equation, and meet your budget of $400,000. There's your first step done. Stating what you want to achieve based on what sort of constraint. Step 2. What is step 2? We're going to create this Lagrange equation. So your Lagrange equation, which is made up of 2 parts, your independent variables, I should say, and your lambda term, which is going to be equal to, and lambda we're going to interpret today as well for this tech question. This whole Lagrange equation is going to be equal to the function you want to minimize or maximize. In this case, it's this function here. Plus lambda multiplied by your constraint, right? Set equal to 0. So over here, I actually have not yet set the constraint equal to 0, but you can imagine I'm going to bring 400,000 to the other side. And so this becomes 40x plus 80y, and I'm just going to squeeze in minus 400,000. So you want to set your constraint equal to 0, so you move this 400,000 to the other side. Okay, so there is step 2 done, or partially done. We're going to expand this out. So let's do that. plus every term here will be multiplied by lambda. So 40x times lambda is 40x lambda, plus 80y times lambda is 80y lambda, minus 400,000 times lambda is 400,000 lambda. Okay, there's your Lagrange equation. It's an equation that considers not only the function you want to maximize, but the constraint that's attached to it. Okay, now based on this overall equation, you want to know where is it maximum. So how do we find that? Probably occurs where it has a critical value. So let's solve for its critical value. Okay, so I'm going to solve for the partial derivative of x, then y, and then lambda. Okay, so partial derivative of x, here we go. Where there's an x, you're going to do it per normal. So there's an x here, you're going to do it per normal. 0.8 will go to the bottom. 0.8 times 50 is just 40x, and the power less 1. 0.8 minus 1 is negative 0.2. Okay, what do you do with y to the power 0.2? You treat all other variables like a number, and like any other number, it will, in this process, come along for the ride, right? And so it will come along for the ride as so. So with this, with these other variables, it will either come along for the ride, as it's done here, or if it was by itself, you treat it like a number, and the derivative of any number will just be 0. So those are the only two things it will do. Okay, there's an x here, so let's talk about this in maybe a more easier way. Derivative of x is just 1, and like any other number, 40 and lambda comes along for the ride. Or if you'd like, what's the derivative of 40x? Derivative of 40x is just 40, because like a number, 40 comes along for the ride, right? Or like this, lambda is a number. What's the derivative of x lambda? It's just lambda, because like any other number, lambda comes along for the ride. Okay, there's no x here, so all this is a number to us, 0. There's no x here, all this is a number to us, 0. So we're going to set this equal to 0, and in this case, you could solve for x or y, but you got to handle these powers. We're going to instead take the road of least resistance and solve for lambda. So we're going to move all this to the other side. So this becomes 40 lambda is equal to negative 40x, negative 0.2, y 0.2. Okay, now we want to get lambda by itself. We're going to divide both sides by this 40. So I'm going to skip a small line here, but maybe you can forgive me. Can I just say negative 40 divided by 40 is just negative 1? Right, so negative 40 divided by 40 is just negative 1, or implied 1. So negative x, negative 0.2, y 0.2. Okay, there's your lambda value. I'm going to call this lambda 1 because soon enough I'll be developing another lambda equation. This one is not really ideal because there is two unknown variables here, and it does look a little bit messy, but we may be able to clean it up a little bit in the next part. In the meantime, let's solve for the partial derivative in respect to y. Okay, partial derivative in respect to y. So now we're focusing on this y. There's a y here, so let's do it per normal. 0.2 we're going to bring it to the bottom. But here's the thing, I'm not just going to bring it to the front of y, I'm going to bring it in front of 50. So 0.2 times 50 is just 10 x, or x to the power 0.8 you just treat like a number. And like any other number, it comes along for the ride. And then we're going to finish off the derivative here, y, and the powerless 1. 0.2 minus 1 is negative 0.8. So if you're not confident with negatives, do use your calculator. No shame in that. Plus, there's no y here, so all this is just a number to us, 0. There's a y here. So derivative of y is just 1, and like any other number, 80 and lambda comes along for the ride. All this is just a number to us, so it's just 0. So we're going to set it equal to 0, and we're going to solve for lambda for similar reasons. So we're going to move all this to the other side. So this becomes 80 lambda is equal to negative 10x, 0.8 y, negative 0.8. Okay, so we want to solve for lambda now, so that will require us to divide both sides by 80. So lambda is negative 10 divided by 80. And again, just forgive me for maybe skipping this small step. Can I just say negative 10 divided by 80 is just negative 1 over 8. Okay, then we've got x to the power 0.8, y to the power negative 0.8. I should say. Okay, we got our second lambda equation. So we've got now two lambda equations. Both are not very ideal, but since we've got two of them, maybe we can cancel things out by setting one lambda equal to the other lambda and see what remains. So I'm going to set lambda 1 equals lambda 2. Okay, so let's do that. So we've got negative x, negative 0.2, y 0.2 is equal to negative 1 over 8 x 0.8 y negative 0.8. Okay, so what are the obvious things that we can cancel out? So the first one we can probably cancel out pretty easily is just these negative numbers. Gone, gone. The second thing, it's not as obvious, but there is a strategy here. I'm going to focus on these negative powers. Okay. So with these negative powers, I'm going to try to get them to be equal to 0. So for example, how do I get this one equal to 0? I'm going to multiply this one, right, this is my multiplication sign, by x to the power of the anti of negative 0.2. So the anti of negative 0.2 is positive 0.2. Okay, so let's see what's going to happen. X to the power negative 0.2 times x to the power 0.2, the base is the same, you just add the powers. Negative 0.2 plus 0.2 is 0, right? And that will simplify more, but we'll leave it there for now. We're going to do the same here, but the thing actually before we move on, I can't just do it on this side, this multiplication. To keep things equivalent, I got to do it on both sides. So I'm going to multiply on both sides, where BS stands for both sides for me, of x to the power 0.2 on both sides. And similarly here, I want to get this one to 0, so I'm going to multiply this by y to the power of anti of negative 0.8 is 0.8. So let's multiply on both sides by these numbers here and see the end result. So here we go. X to the power negative 0.2 times x to the power 0.2, the bases are the same, so you can just add the powers. Negative 0.2 plus 0.2 is x to the power 0. Y to the power 0.2 times y to the power 0.8, the bases are the same, so you can just add the powers. 0.2 plus 0.8 is y to the power 1, which is equal to 1/8. X to the power 0.8 times x to the power 0.2, the bases are the same, so you can just add the powers. 0.8 plus 0.2 is x to the power 1. And here we go. Y to the power negative 0.8 times y to the power 0.8, the bases are the same, so you can just add the powers. Negative 0.8 plus 0.8 is y to the power 0. Okay. So remember here, anything to the power 0 is just equal to 1. So this really just breaks down pretty easily. Okay. Anything to the power 0 is 1. So this becomes y, which is equal to 1/8 x times y to the power 0 times 1. Okay. So there's our equation for y. So we can solve for y as long as we know x. So this, I guess, is an ideal equation and something we can probably utilize pretty soon. Let's now solve for the partial derivative in respect to lambda. Okay. So where's our lambda value? Let's grab it. Okay, so here we go. Now we're concentrating on lambda. There's no lambda here, or this is a number to us? 0. There's a lambda here. So derivative of lambda is just 1, and like any other number, 40x comes along for the ride. Plus, derivative of lambda here is just 1, and like any other number, 80y comes along for the ride. Plus, derivative of lambda here is just 1, and like any other number, negative 400,000 comes along for the ride. Okay, so we're going to set this equal 0, and remember our tip here, we're usually going to be subbing something into here. Guess what we're going to sub in? This y is equal to 1/8 x. So what's going to happen here? We've already got x here. If we sub in y equals 1/8 x, which is expressed in x into here, we're going to have an equation or an x, and hopefully with a little moving things around, we can solve for x. So let's do that. This becomes 40x plus 80 times y, which is 1/8 x, minus 400,000 is equal to 0. Okay. I'm going to bring 400,000 to the other side, and right, we're going to simplify this. Right, so 40x plus 80 times 1/8. That's basically 80 divided by 8, isn't it? So that's like 10x is equal to 400,000 to the other side. Okay, now this really breaks down quite nicely. 50x equals 400,000. X is equal to 400,000 divided by 50, which is just 8,000 for us. Once we have the first one, we can solve for the other ones in a pretty quick succession. Y is simply 1/8 of x, so it's just 80 times 1/8, or 80 divided by 8 if you wish, which is just 1,000. And we're also going to need to solve for lambda because we'll be interpreting it pretty soon. How do we solve for lambda? We actually have two equations for lambda just over here, right? So you can use any one. They both require x and y, but they both should give you the same answer. So, and in the interest of just saving time, I'll just give you the answer: negative 0.6598. Okay, there's your lambda value. So this is our critical value. Because we only have one critical value, we can actually assume that this represents the solution to the problem. What is the problem? We want to find combinations of x and y that would maximize this equation. These are your combinations of x and y that would maximize that equation. So what is your maximum equation? Into my Cobb-Douglas function, when x equals 8,000 and y is equal to 1,000, you're going to just pop it into your Cobb-Douglas function. You're going to get a value that looks as so: 263,901.58 units. So in theory, this represents your maximum Cobb-Douglas units, right? Given that you've only got a budget of 400,000 to use. So any other combination of x and y would give you a number lower than this number. Okay, that's part A done. Let's go ahead and do part B. Part B reads as follows. Find the marginal productivity of money and estimate the increase in production if an additional $50,000 is budgeted for the production of the product. Okay, so we want to comment on this marginal productivity of money. So the key word there is that. If we want to comment on that, we're going to be commenting on what's known as lambda. So we know lambda is equal to negative 0.6598. Okay, when we interpret lambda, we're going to interpret as an absolute value, meaning we have these two vertical signposts, I suppose. And that means basically we don't care if it's a negative number, we just want to take the number raw. Okay, so the interpretation is this. This represents the number where if you relax the constraint by 1 unit, this is how much you expect to gain in your function of interest. So let's maybe put this in terms of a story, right? So if I relax the constraint by 1 unit, what does that mean? What is my constraint in this unit or in this story? We've got $400,000. That is our constraint. So budget is our constraint. If I gave you 1 unit extra in your budget, what does that mean? It means I give you extra $1. So if I gave you $1 extra in your budget, you'll gain an extra, right, 0.6598 units. That's how much you're going to gain extra. Okay. But I don't just give you $1, of course. How much am I actually giving you? I'm giving you $50,000, right? So how much extra would you gain? 50,000. Well, let's write this as 50,000. Right, that I was about to write 50K, but let's write 50,000 multiplied by 0.6598. Okay, so this will give you 32,000 and what was it? Let me see. 32,990 units. Okay, so that's how much extra you're gonna have if you put in an extra $50,000 in your budget. Okay, that is question 2 done, right? We've only got one more question to do. This represents your final and last question forever in QA. So here we go. Question 3. We all done here? Yeah. 3 pens of the same size are to be built along an existing fence. Okay, so let's check out this existing fence. We have this fence here. There's your existing fence, and we've got 3 pens. Pens is just farming language for 3 enclosures. So we've got these 3 enclosures that we want to build. If 400 feet of fencing is available, what length should X and Y be to produce the maximum area? What is the maximum area? So notice that with this question, it's a little bit more special because no equation is actually given to you, right? We have to derive our own equation. Okay. Look, sounds a little tough, but it does work out quite well, right? So let's take it step by step. So the first step is we want to formulate the problem. So what is the problem here? Step 1. We want to maximize some sort of area, right? So we want to maximize some sort of area function. Where is our function? Well, our area, just according to the picture, can I say it looks like a rectangle, right? What's the area of a rectangle? Can I say it's just length times width, right? Or can I say, just using the picture, can I just say it's x times y, right? So there's your area. So we want to maximize this area function. It has 2 independent variables, x and y, your length and your width, or vice versa, doesn't really matter, which is equal to x times y. There is your area function that you want to maximize. Subject to what constraint? Well, subject to, we only have 400 feet of fencing available. So how do we derive an equation that would tell us, or give us a 400 feet as a constraint? Well, let's maybe look at this picture. how many lengths of x do we have? We got 1x, 2x, 3x, and 4x, right? So we got 4x plus how many lengths of y do we have? We have one long y, right? Plus y. Whatever x and y is, we can put into this equation. We should only meet or require or use, whatever word you want to use, 400 feet of fencing. There's our constraint. We're going to set it equal to 0, right? So this becomes 4x plus y minus 400 is equal to 0. There's our first step, right? And you can imagine this is the most important step. Without this step, you can't really do 2, 3, and conclude. All right, so that is the most important step, but hopefully those equations and the constraint actually make sense on where it came from. Okay, step 2, we want to create this Lagrange equation. So this Lagrange equation is going to be made up of two parts, your indeterminate variables and this lambda term, which is going to be equal to the function you want to minimize or maximize. In this case, it's this xy plus lambda multiplied by your constraint set equal to 0. So I'm going to put all this into brackets. So we got, what do we have here? 4x plus y minus 400. Okay, let me actually use this full screen now. That's a bit better. Okay, guess what we're going to do here? We're going to expand this out. So this becomes xy plus every term in here will be multiplied by lambda. 4x times lambda is 4x lambda plus y times lambda is y lambda minus 400 times lambda. Okay, there's your Lagrange equation. What's our aim here? We want to find where's the maximum point of this equation that not only considers your area, but it considers your constraint, right? It's like an all-in-one equation. So we know those will probably occur where it has critical values. So we want to, and this is where you guys are going to go off. I want you guys to solve for the critical value of x, or the partial derivative in respect to x, the partial derivative in respect to y, and then the partial derivative in respect to lambda. Okay, there's two ways you're going to go about this. If we solve for this, you could solve for y and get an equation. You could solve for x and get an equation, and you can plug these into here, right, and then solve the rest. Or if you prefer this, you can also solve for lambda 1 here, you can solve for lambda 2 here, and then you can set these equal to each other. You can set lambda 1 equals lambda 2, and then whatever resulting, you can also plug it into there, right? Generally this is preferred when it is available, but like that Cobb-Douglas function, sometimes you just have to do it this way. Okay, this is where I leave you to it. I'll be walking around to provide some final feedback. If you've got any assignment questions, do leave them to the end of the class or close to, and we'll address them together. In the meantime, let's all make sure that we do this correctly and properly, and then we're going to call it a day, at least from a tutorial perspective. All right.